So welcome to this seminar in ICP Calibration. My name is Magnus Roman. I'm working for Technolab Sorbent in Sweden. We've been a partner we've been in partner with Inorganic Ventures for almost 2 decades, and we are very happy to, for this first time, do a webinar with our customers here in Sweden. It will be a 45-minute seminar with some question and answers at the end. And I also want to say, if you have any, I hope for the future we can do more of seminars like this. And if you have any wishes or ideas of what you would like to hear, please send me an email afterwards. And I think also we will send out a questionnaire after the webinar. We didn't talk about this beforehand, but I hope we will, where you can give feedback if you have pros and cons and so on. So I have here Dr. Lesley Owens, who will hold the seminar for us about ICP calibration. And I leave the word to you. Lesley, please.
Thank you, Magnus. And thank you all for joining the webinar today. What I would like to discuss with you today is techniques and tips for improving ICP calibration. A good way of improving calibration is by improving the stability of your calibration standards. Without stable working solutions, your analysis will suffer. Today's talk will focus on the key considerations for designing calibration solutions and how to prepare and handle these solutions. Then we will shift gears a little and discuss potential causes for unexpected results and provide basic information for troubleshooting these problems. The intent of this portion of the presentation is to provide information that applies to commercially available materials as well as tips for making your own working solutions. Inorganic Ventures has been designing and manufacturing reference materials for 30+ years. So our experience during these years has given us a broad body of knowledge, and this presentation will draw from that chemical expertise. Inorganic Ventures is an ISO accredited reference material producer, or RMP. So during our 30+ years, we have approved about 57,000 solutions in our database. So these solutions vary from single element standards to common multi-element standards like tuning solutions. We also can supply very complex materials. So we're talking standards that have trace levels of certain elements and high or matrix type levels of other components. So these mimic real world type samples. We do specialize in designing custom products and enjoy the challenge associated with custom blending. Our standards are NIST traceable and are provided with a C of A, and the C of A will give you the certified value as well as the associated uncertainty. The certification method used will vary based on the product and or the intended use. So for example, a titrant is not certified in the same manner that a stock ICP standard is certified. In general, ICP users have 2 options for calibration standard preparation. First is to purchase ready-to-use solutions from an RMP, or you can make dilutions of commercially available stock solutions. Okay, this could be a custom solution that a certified reference material producer makes for you, or it could be straight off the shelf stocks. The table here shows a comparison of each method, so some advantages and disadvantages of both approaches. In general, there's no one-size-fits-all approach, and the choice should be what we consider fit for purpose. So it needs to make sense for your individual lab. So some factors that will go into deciding whether you're using ready-to-use solutions or making your own include your lab's analytical goals. the budget that you have, your level of accreditation, the audit protocols, you have the level of training of your staff, the equipment that you have, and so on and so forth. Most labs typically fall into the second category. We do have customers that purchase ready to use, but most of our customers are buying some stock and then making dilutions into their working solutions. So this is the reason why I would like to discuss tips and tricks for designing stable working solutions. Regardless of the approach that your lab takes, there's some key considerations that go into designing calibration standards. First, I'll talk about inter-element compatibility, which that's just talking about which elements get along with one another, and those that may need a little special attention. Okay? Then I will describe how container properties influence solution stability. And then finally, I will discuss how the solution matrix plays a role in working standard design. For most of the information that I'm going to share with you today, these have been our lessons learned in our laboratory. So as required by ISO, we have a stability program. I consider our stability program to be very robust, and we use the data that comes out of this program to create solutions that are considered to be stable by design. All right, first up, we'll talk about inter-element concerns. So inter-element compatibility must be considered when designing stable CRMs. The following guidelines are observed at Inorganic Ventures. We have a standard operating procedure for the quote process that includes everything that I'm talking about today. So we follow these when we're creating custom multi-element standards. First off, the presence of potassium and silicon at concentrations greater than about 200 ppm can cause the formation of a gel in your solution. So the problem here is you don't recognize that this gel has formed until you go to pour your solution out of your flask or whatever container you've prepared in. And by that point, it's too late. So if you have potassium and silicon in your analysis, be aware of this particular gel formation. Cesium is also a problematic element in the presence of platinum and uranium. Okay, you can get precipitation of cesium if you're trying to blend cesium and platinum together. So you'll have platinum and cesium both fall out of the solution as this cesium chloroplatinum type complex. For rhenium, this is concentration dependent. So if you have concentrations greater than about 2,500 ppm, you can see precipitation of a complex with cesium and rhenium. Chromates can be problematic as well. So if you have chromium in your system and you're using a chrome 6 starting material, you could have problems with elements such as lead, barium, and thallium. So what we typically advise here is to avoid the use of chromium 6 in your calibration standard. Instead, we recommend that you use chromium 3, right? So your ICP will not be able to tell the difference of chromium 6 versus chromium 3. It's all total chromium when it's in your ICP. So we recommend switching over to that chrome 3 starting material, and you won't have a problem with lead, barium, or thallium precipitating as a chromate with those situations. We also can have issues where carbon sources are involved. So carbon as an element, or if you have carbon coming from the starting material. Beryllium, for example, uses an acetate starting material for the beryllium solution. So carbon sources and carbon by itself will cause a reduction for problematic elements such as mercury and palladium. So you'll get a reduction of those elements to the metallic form in the presence of a carbon source. So be careful when you're blending things that contain carbon and your mercury and palladium. Then finally, ratios of certain elements are should be considered when you're talking about contamination type issues. So geochemical twins are the easiest example that comes to mind when you're talking about this. So elements such as zirconium and hafnium, niobium and tantalum, and molybdenum and tungsten are going to exist in nature as combined type ores. So when you're doing an analysis for zirconium and you also have hafnium in your system, you want to make sure that you're not seeing an increased contribution of hafnium from your zirconium starting material. So it's important to consider the purity of the material that you're working with. The composition, cleanliness, and matrix compatibility of the preparation and storage containers that you're using are also important considerations for maximizing CRM stability. So LDPE, or low density polyethylene, is the most commonly used container type at Inorganic Ventures. This is because it's the cleanest and it provides a broad range of solution compatibility. So we can put a variety of different solutions into an LDPE container. Also, we can utilize a specialized leaching process to ensure an even cleaner bottle for low-level solutions. So we call these HEPA blends. So these are solutions that contain elements less than or equal to about 100 ppb. Okay, so when we're dealing with solutions on a low level, we prepare these in a clean room, and we also use these extra clean bottles. We have no issues with HEPA level blends containing common contaminants, so calcium and sodium, for example, when we're using this process. So a clean bottle and also clean starting material are very key when you're trying to work in low levels. Okay. So LDPE is our bottle of choice, but there are some instances where LDPE is not recommended. So examples include mercury at concentrations less than or equal to 200 ppm, and or palladium less than 100 ppm when you're working with a nitric matrix. We don't see this problem when we're working with HCl. So mercury and palladium and HCl is fine in your LDPE container. However, if you need a nitric matrix, you're going to need to switch to the borosilicate glass to ensure stability. So without the use of borosilicate glass, what happens is you get an adsorption of the mercury or the palladium onto the surface of your plastic container. And the use of borosilicate glass prevents this adsorption phenomenon. Okay, so there are some instances where borosilicate glass should not be used. One of them is in the presence of HF. Okay, so HF can attack the glass, and what you'll see is a leaching of boron and silicon into your solution. So if you have boron and silicon already in your calibration standard, you're going to see an increase. So it's not going to have the same concentration that you think it does. Also, you can have issues with HF and glass sample introduction systems. So it's the same type of effect where you'll leach boron and silicon from your sample introduction system, and then you'll see your background increase for those elements, and it will ruin your results if you're trying to analyze those particular elements. So additionally, common contaminants in boro limit the use of several elements. Okay, so we have a varying degree of contamination for the elements shown in this list. So we have recommended lower limits for glass use. That tends to be higher for elements like aluminum and sodium, and lower for elements such as strontium and gallium. It's just the different level of contamination of each element in borosilicate glass. Okay, so now we need to talk about matrix. So the most commonly used Matrix components are the mineral acids. So we have nitric acid, we have hydrochloric acid, and we also use hydrofluoric acid. So the combination of elements and concentration influences the matrix selection for stable CRMs. So this slide talks about the limitations for each of those matrix types. So first, nitric. Nitric's the most commonly used matrix. So some key considerations here are antimony stabilized in tartaric acid. So with this type of stabilization, you want to keep the nitric matrix low. So we're saying less than 2% volume to volume from a concentrated nitric. What happens here is as the nitric concentration increases, it has a destabilizing effect on antimony. So what we say is it chews up the antimony, the tartaric complex rather, and then that destabilizes antimony. So you want to avoid using the tartaric if your matrix has to be greater than 2%. You can switch over to the antimony HF solution at that point. Some situations require high levels of nitric acid. So situations where you have arsenic, bismuth, and lead all in one solution at a concentration of 1,000 ppm or more, we're going to require that that has 15% nitric or more. And that's to ensure that those elements remain in solution. Gold is a problematic element in a nitric-only matrix. So if you're using gold, you want to make sure that there's some level of chloride associated with gold so that you stabilize that element. So speaking of HCl, so we do have issues with osmium, but not in the HCl matrix. So we recommend that you use an HCl matrix only when you're working with osmium, and that's to avoid the formation of the toxic and volatile tetroxide complex. So in order to avoid that, you want to stay in an HCl matrix. Also, silver can have issues with HCl. So silver in the presence of chloride is photosensitive, and it will precipitate at trace levels of chloride. Okay, so what you want to do here is, you can see the formation of the crystals when you're adding a trace level of HCl to silver. So what we do to avoid this is overwhelm the system with chloride ions. So we're talking 10, 15, 20% HCl when you have certain levels of silver in your system to overcome this precipitation. Okay. You also want to avoid the use of thallium+1 in HCl matrix. So you'll need to be aware of the state, the chemical form of thallium if you want to use that in an HCl matrix. We recommend the +3 state for stability in HCl. And then finally, we have HF. So there are elements that are HF sensitive, meaning you don't want to combine an HF matrix with these elements. The most severe example is the rare earth elements. Typically, you want to stay away from any HF with your rare earth elements. The group 2A elements are a little more tolerant of HF up to a certain concentration. Thorium, same sort of category as the group 2As. And then chromium 3 has a little bit of a higher tolerance for HF. You know, for your group 2As, we're talking, greater than 100 ppm. You don't want to put those with HF. Thorium, the guideline is about 10 ppm. And then your chromium can increase to about 500 ppm, chromium 3, when your HF increases to 1–2% levels. Our PPB stability study, which was conducted and published by Dr. Gaines on our website, can give you an idea of the length of stability that you can expect when you're combining several stock solutions. So in this particular study, 65 elements were combined using our CMS set of elements. These are stock solutions for us that contain as a set 65 elements. So what we did was we combined these 5 standards into a matrix of 1% nitric acid at concentrations ranging from 2 ppb to 100 ppb. Okay. As you can imagine, given the information that I've already spoke about, some elements are more stable than others in this configuration. So you see that we have the rare earth elements in the CMS1 set, and we also have HF coming from that CMS3 set. So that's an example of elements that would have problems in this solution. So overall, there's too much information in this study for me to cover in this slide, but what I do recommend is that you visit our website, and the link is shown here on the bottom to get more details about this expected stability. It's a really good resource if you're having issues with stability in your particular working standards. Okay, in this section, we're going to discuss the proper ways to handle, store, and prepare your working solutions. So first off, let's talk about the actual design or the creation of your own standards. As I mentioned earlier, the majority of our customers will create working solutions from our products in some form or fashion. So in general, what we recommend is a gravimetric preparation. And this is what we do in-house also. So we do a gravimetric preparation as opposed to a volumetric preparation. So we're using an analytical balance and weighing out an aliquot of our material to ensure that we're not having issues like an air bubble from our pipette or an issue with the viscosity of a solution. So in general, we feel that pipettes aren't suitable tools for highly accurate and precise work. And instead, we're going to use the analytical balance to weigh out the aliquots directly. Okay? So what we do is we weigh onto a weigh boat, and then quantitatively transfer into the solution, or as shown in the picture, you can weigh directly into your final bottle and then bring that to a final weight based on the solution density. Okay. The bottles that we use, I mentioned earlier, we're talking about the importance of using clean bottles. We use a 1 to 5% nitric acid solution for bottle leaching. So essentially we're filling up our bottle, letting that sit for a while, and then discarding that solution and making sure we're rinsing several times to ensure that our bottles are clean. Again, we're using LDPE and a 1 to 5% nitric for our leaching procedure. So that generally gives a very clean bottle for the type of work that you would need for ICP analysis. So the usage period is a key point for labs, right? You want to make sure that you don't have to do this every time. You don't have to go through the process of making working solutions every time you want to do an analysis. So having some level of stability in your working standard is important, right? So based on the analyte concentrations, the matrix, and the container, as well as your storage conditions, the usage period of your working solution that you've prepared can vary. So in general, what we say is that working solutions shouldn't be used for longer than a year at a time. So this is going to be the customary expiration period that you see for most materials on the market. There are a lot of things that can happen over the course of a year, gross error, contamination, you have factors such as transpiration to worry about. So in general, if you can get a longer stability, that's great, but typically don't hold these longer than a 1-year period. You can do what I call a pseudo stability study to be able to establish an expiration date of your calibration standards. So what you would do here is take an aged solution and compare that head to head against a freshly made solution. So you don't have to use a calibration, you're just using raw data to compare the material. So what you do is you do a statistical analysis on the two data sets, and you're looking to see if there is a difference between the two data sets. If you don't see a difference in the data set, then you can assume that the solution is stable. Okay, and then you can apply that solution's age as the expiration date to your calibration standard. So you can do this, a series of times until you get the desired expiration date that you're looking for. So virtually all Inorganic Ventures products are packaged in either low-density polyethylene, LDPE, or borosilicate glass containers. So we've done our own studies on 125 ml bottles, and the table shows the level of impurities that we found in the different container materials. So this is something that you could be aware of when you are preparing your own calibration solution. So it's not necessary to use the expensive Teflon bottles based on the data that we have found in this particular study. Unfortunately, our concentrates and subsequently your concentrates have a finite concentration. So most of these will cap out at about 50,000 ppm. Some of them are on the lower end, like 1,000 ppm, such as osmium, and others can range to maybe 120,000 ppm. Calcium, for example, can go that high. It's all based on solubility and stability of the material. So as a result of this limitation, there are volume considerations. So basically you can't fit more than the total flask volume while you're preparing your aliquots. So basically the takeaway here is that the number of elements per solution decreases as the concentration increases. So as you can see on the right, at 10,000 ppm for all of the analytes in your calibration solution, you're not going to be able to fit more than about 5 or so in one solution. And as you decrease down to something like 10 ppm, we're starting to get the majority of the periodic table can fit into your calibration solution. Again, we need to be mindful of the other stability rules, but you're starting to be able to prepare large working standards at this point. Over the years, we've found that order in which we combine elements impacts the overall solution stability. So we refer to this as order of additions. Typically, we start each solution with a mixture of water and acid at a 2-to-1 ratio. Then we add all the aliquots by quantitatively transferring them to the flask, swirling your flask in between each addition, so that we prevent any sort of exposure to a localized high concentration, either of the acids or the elements or a combination of the two. So we have some examples we can share for compatibility issues that we can remedy with a change to the order of additions. So first is osmium. So adding osmium last in the presence of other analytes that will carry over a lot of nitric acid from their stock solution, when we add that osmium last, we're going to prevent the localized high concentration of nitric. And then in turn, what we do is we prevent the formation of the volatile and the toxic tetroxide. Okay, again, this is working in an HCl matrix, but using other stock solutions that would have a high nitric load. Okay. So another example, and the one shown in the photograph, is HF-sensitive elements. So we talked about the group 2A elements being HF sensitive and also your rare earth elements. Okay, so this particular photo is showing you the precipitation of calcium fluoride. So we've added calcium in the presence of HF, and on the left, you can see that you have precipitation of calcium fluoride in this solution. So it's not stable and it won't work in your calibration solution. So The photo on the right, what we've done is we've switched up the order of addition. So what we've done is added the calcium last when the solution is very close to volume, and we've diluted out the majority of the HF matrix. And what you can see is we've prevented the formation of that fluoride salt. Okay, so order of addition, really important when you're combining your stock solutions to make your calibration solutions. If you're using commercially available CRMs, the C of A is going to provide information regarding proper storage and handling, but in general, the information on the slide is good practice for those lab prepared solutions that you can create. So in general, we say store at room temperature. So we're saying 20 plus or minus 4 degrees C. Or below. Refrigerated storage is not required, but it can't hurt, and we'll see that in just a minute. The next 2 bullet points are talking about contamination. So what you want to do is you want to pour out of your stock bottle into a secondary container and then pipette from that secondary container. That's to prevent you from putting any sort of object into your stock bottle and contaminating. Also, any leftover material should be discarded. You don't want to pour that back into your stock bottle as well. We've seen photosensitivity with silver, so you want to make sure that you're not storing your standards in direct sunlight. For solutions containing silver and in an HCl matrix, we actually recommend storing that in a dark place and avoiding any sort of light interaction when you're working with that material. You want to make sure that you keep your cap secured when not in use. I don't mean to over tighten the material. Just make sure the cap's on there finger tight. That's good enough. We'll see in the next slide why it's important not to over tighten your cap. This also prevents the oops factor. So your clumsy lab mate comes around and knocks your bottle over. You don't lose your solution. And it also prevents environmental contamination. So say a chunk of ceiling tile falls into your bottle. So you wouldn't waste your expensive solution at that point. If you have any questions on the safety aspects of handling your working solutions or your CRMs, then you'll need to consult the safety data sheet. Okay. So in this slide, I want to talk about transpiration. I mentioned it earlier when I'm talking about the expiration of your working standards. So basically, transpiration is the passage of water vapor from your solution to the outside environment. So this happens around the cap as well as through the walls of your container. What you see as a result is a systematic increase in concentration over time. So at some point, the certified value, you'll exceed the uncertainty component on your solution as your bottle transpires over time. So what we've done to prevent this is the use of a transpiration control technology bag, this TCT bag shown in the picture. So what happens here is it's an aluminized overpackaging that creates a microenvironment for that equilibrium to be established for transpiration. So what this gives us is the ability to put a 4-year lot expiration on our materials. After you open the TCT bag, the customary 1-year usage period comes into effect. But you can store multiple bottles in your facility and not have to worry about things like temperature or validating new calibration standards every time. You've got the same lot over and over through the use of extended expiration and TCT. So this is a benefit for our customers. So issues affecting transpiration. So one, bottle size. So smaller bottles we found transpire faster than larger bottles. Also the fill level of your solution. So as your fill level decreases, the rate of transpiration will increase. Temperature, I mentioned that 20 plus or minus 4 is the usage temperature. So as temperature increases, your rate of transpiration will increase. And then finally, torquing. So this one is interesting. There is a sweet spot for the torque on your bottle. So the data here looks like a Nike swoosh of sorts. So you have at too low torque, or it's not capped tightly enough, you'll have an increased rate of transpiration. And then on the other end, once you over tighten, you can deform the matching between the cap and the threads of the bottle, and what you'll see is an increase in transpiration. So just make sure your finger tighten those, and you shouldn't have to worry about transpiration if you're following a 1-year usage period. Okay. So in the remaining time, what I would like to do is shift into the second part of the presentation and use this as a discussion on ways of troubleshooting unexpected results. So before we get into the specifics of troubleshooting, it may be beneficial, which I think it is beneficial, to review the importance of instrument tuning. Okay, because the quality of your results will only be as good as the performance of your instrument, and tuning will help ensure proper function. Okay, so on the slide are basic goals for tuning. So on an ICP OES, what you're looking for in your tune is a high intensity of your elements that you're looking at, as well as low RSDs. So you want a good precision coming out of your instruments. So on the mass spec side, you want to see the same things, but in addition, you want to make sure you're seeing low oxides, and you're also seeing low doubly charged species on your detector. All right, so what I've given here are ways of troubleshooting your tuning to ensure that you're getting adequate performance from your instrument. You can spend a lot of time tuning when it's not necessary. I want you to remember here that your tune only has to meet your performance checks. So if you don't need a highly tuned instrument, don't spend your time tuning when it's not part of your performance. So your method validation activities should give you an idea of what performance you should expect for your instrument. Okay. So here we're going to walk through the different types of calibration errors you could see. So as part of this troubleshooting section, I'm going to discuss potential causes and ways to remedy the error that you see. Okay, so we'll talk specifically about situations where you get no results. Your results may be lower than expected, or you have higher than expected results. Okay, so you have gone through the process of ensuring that your working solutions are stable, you've got your instrument tuned properly, and then you go to run your analysis and realize that you're not getting any results. So this is a bit concerning, and you can feel defeated when this happens. But typically, when you see no results, this is going to be commonly related to maintenance type issues. So what we recommend is you take your system down to the most basic elements and then build back in complexity as you progress through your troubleshooting. So a lot of sample introduction systems can be complex with syringe drives and auto dilution type systems. So here, just take it back to the most basic components and then start building back in as you troubleshoot. So in general, pump tubing is a common culprit for issues relating to no results. So your tubing can become stretched and it can even detach from your system. So replacing and checking your pump tubing is really a cheap and easy fix for these types of problems. Also, your nebulizer. So concentric nebulizers are commonly used, but they suffer from clogging more than other designs. Recently, there have been some improvements in the ability of a concentric nebulizer to handle high total dissolve solid load, but in general, other nebulizer types may be better for your analysis if you're running high TDS samples, or your analysis contains high TDS components. So another nebulizer like a crossflow may be more appropriate for those situations. Okay, so what to do if you have a clog? So you can clear a clog by forcing water through the nebulizer, so just flushing, or you can do a process called back flushing. So you're going to flush in the opposite direction of the normal flow. There's a special tool that comes with your nebulizer, so you would want to use that if you're looking to back flush or clean your nebulizer. You don't want to stick anything into that nebulizer, and we also don't want to sonicate your concentrics. You know that the inner glass is very fragile, and you might cause damage that way. For stubborn clogs, what we recommend is soaking your nebulizer in dilute acid, or for extra tough clogs, we can soak our nebulizer in a commercially available detergent. We use a 2.5% solution of a detergent called RBS 25. Okay. We have, once you think your clog has been resolved, you can do a quick sodium or yttrium bullet test to see if solution is flowing through your system appropriately, or you can look at the counts of your internal standard to see if you're getting proper sample delivery now. Another issue that could result in no results is improper peak centering. So what we recommend here is that you actually go into the spectral window. So don't rely on what's coming out of the instrument. Look at the actual, the peak and what's going on in that window. And you just want to confirm that your positioning is correct and that you fully understand any background corrections that your software is applying. Right? So some of these can be a little bit of a black box per se. So if you don't know what's going on, we recommend you contact the instrument manufacturer to figure out what's going on, or that you don't use any of those sort of corrections. Another word, most users tend to be afraid of raw data and spectra for some particular reason. But we think this is really good information to use when you're trying to troubleshoot a problem with your ICP. So don't be afraid to get into those spectral windows, to look at the raw data and try to figure out what's going on. Another sample introduction system problem that could result in no results would be improper wetting of your spray chamber. Okay, so what can happen here is you can get large droplets to form in your spray chamber. So that usually happens when your solution's not flowing through the spray chamber like it's supposed to. Okay, so your nebulized solution starts to bead up or collect in your spray chamber, and then generally your plasma will extinguish in those situations. If your plasma does remain on, your results are going to be inconsistent. Your signal stability is really poor, and what happens, you'll have your precision will become problematic. So you'll have poor precision as a result of this improper wetting. So problems with the drain can also be a reason why your plasma extinguishes. So it's really easy. Check to make sure that your drain is functioning properly and that the solution is coming out of your spray chamber and to the waistline properly. Many torches have been melted as a result of an improper drain connection. So that's an easy place to look to troubleshoot if your plasma is having problems. Also, you know, differences in viscosity volatility of your sample and your solutions may cause issues with your plasma extinguishing as well. Another cause of subpar instrument performance could be issues with the gas flow. We saw on the other side in your tuning, just to make sure that your gas flows are appropriate. So that's your nebulizer and your plasma gas flows and any tubing associated with those components. Okay. So we recommend running a retune if you're having issues with your results not coming out properly. You can perform maintenance also, or daily maintenance or preventative maintenance. So general maintenance, this is something that we do at Inorganic Ventures. This is an example of our daily, weekly, monthly type schedule. You can think of maintenance acts as an insurance policy, which gives you peace of mind because maintenance is going to help reduce the likelihood of problems in the future. So this is an example of what we do. You know, it really depends on your sample type and how aggressive you need to be in cleaning on a daily basis. So this is just kind of a guidance for what we do. So low results can happen when your calibration standards are mixed improperly, or you have a stability issue. So for the mixing, we talked about, you want to make sure that you're inverting your solution. We prefer the inversion method for mixing. So what you want to do is make sure that air bubble travels the full length of the container that you're working with. So we prefer inversion, and typically 50 over and back is what we do when we're mixing a flask. For mixing, all of your analytes will show up low. Stability, not all of your analytes will show up low. If you're having a stability issue, this is usually one way to figure out that, to hone in on the fact that it could be a stability issue, is if one or a group of elements are low. So what we would recommend here is to make sure you're assessing the stability of your working solution. If you're using those over a period of time, make sure that you're following the kind of the guidelines that I set forth in the beginning of the presentation to ensure that you have the most stable situation possible. Okay. And then high results. So this one is also a little bit troubling, is you're getting a result that comes out a little higher than you expect. So potential causes could be transpiration with your solution. It could be an interference in your analysis, or it could even result from a washout issue. So you had something that it was stuck on your tubing, and now all of a sudden it's part of your solution flowing through when it's not actually part of your analysis. For transpiration, we recommend storing according to the manufacturer's recommendations, or the recommendations you would typically see from a manufacturer. We know that refrigeration is not necessary, but there's nothing wrong with storing your solutions at a lower temperature. So just one note of caution when you're handling solutions that come out of the refrigerator is you want to allow that material to come to room temperature and mix that thoroughly before you start using it. You'll see everything low if you don't mix that thoroughly. So if you're trying to avoid transpiration, you could also end up with a situation where your analytes are low unintentionally. Just let that come to room temperature and everything will be fine. The interferences, just understanding what's in your sample and your standard will help you overcome any interferences. Also your method validation activities will help you with interferences. Another thing, if you're suffering terribly from oxide interferences, a temperature regulated or temperature controlled spray chamber can help in those situations. So at lower spray chamber temperatures, you see fewer interferences. And what you'll get here is improved detection. You'll have a longer term stability of your signal, and your calibration results will improve if you're having issues with that. And then finally, washout issues. So sticky elements tend to be problematic. So your boron, your molybdenum, mercury, for example. And we also have washout issues associated with the age of our HF resistant spray chambers. So what our spray chamber that we use has a coating on the inside, and depending on how much solution we have containing HF that we're analyzing at one time, we can see kind of a degradation of this surfacing, and we need to send that out to get that resurfaced periodically. And again, the resurfacing just depends on the nature of your analysis, how many samples and the type of sample that you're analyzing. Okay, so just to a final thought on troubleshooting is how do you confirm your results? So you think the the result is high, low, or it's just not there. What can you do? So typically most methods are going to prescribe the use of some sort of confirmation tool. So a second source check solution, for example, can confirm the performance of your calibration, and also the use of RMs. You can verify proper performance of your calibration using a reference material. So it's a known concentration coming from an outside lab. Okay. Standard additions you can also use if you have interferences, so you can spike things in to see if peaks grow, which is shown on the right. But in general, what we recommend is you really get into that raw data. So the raw spectra or the counts coming out of your instrument. Don't rely on calibration and calculations going on. And finally, if you're at a loss, contact reference material producer this is where Inorganic Ventures can come in. We have a variety of resources available on our website. We have an education section shown here. The interactive periodic table is great for things like storage and handling of particular samples, how to get certain samples into solution. We have a forum where you can ask questions regarding problems you're seeing in your lab. And just a variety of a good wealth of knowledge there. And then finally, technical support is available. You don't have to be a customer of Inorganic Ventures to get technical support from us. So I encourage you, if you're having issues, to contact Magnus or get in touch with us and see if we can help troubleshoot the problems that you're experiencing. So I thank you for your time and your attention, and I can take questions.